Okay, the focus of Chapter 5 is going to be pretty much quadrilaterals. That's going to be the main thing that we're taking a look at. A quadrilateral is just a form of a polygon. It's a four-sided polygon, essentially. So here we have a five-sided polygon. What we're going to start by taking a look at is the sum of the interior angles on these polygons. We're going to take a look at how many degrees are there total. So for instance, what we saw before is that in a triangle, there are 180 degrees for the interior angles. So let's break this up into a few different triangles, knowing the fact that we have 180 degrees. We're going to do that by drawing a diagonal. Alright, so the diagonal is just basically going to be connecting one of the different vertices to the non-consecutive, so the ones that are not right next to it. So if I start from the vertex B right here, I would connect it to E. I would also connect it to D. I'm not going to bother connecting it to C or D because those are going to be consecutive ones. So as a result, what you notice is we've created three different triangles. All right, and knowing the fact that each triangle has 180 degrees for the internal angles, we know that if we add those up, 180 plus 180 plus 180, that's going to be 540 degrees of internal angles right there. With this concept in mind, we can figure out a number of different sums of angles for these different types of polygons. Once we get past 9, which would be a nonagon, we're just going to call it n-gon. So we'll replace n with the number of sides that we have, which we'll see in a few examples a little bit later on. The important part of this section is going to be that we're drawing convex, which basically means there's no sides that end up pointing in. Everything is outside. So not concaved is the main thing for here. If we do that, that's going to give us a little bit different of a scenario, and these things will not quite work out. Alright, let's take a look at a quadrilateral. So a quadrilateral is just going to be a four-sided figure, and like I mentioned, that's going to be the main focus later on in this chapter. So it doesn't have to look like anything special, just draw a four-sided figure. Convex, so none of the sides are going in. We take a look at it, we're going to see how many triangles we can get out of that. Alright, just drawing the non-consecutive vertices, I get two triangles. So four sides results in two triangles. And we know that's 180 plus 180 is going to give us 360 degrees. Okay, and that's 360 degrees for those internal angles. Just like we saw for a triangle, there's 180. For a pentagon, that's going to be a five-sided figure. So let's draw that up really quick. Five-sided figure. Alright, after we have that, so the number of sides, first of all, is going to be 5. Let's see how many triangles we can create on that. It's much like the first example we took a look at, so I know that I can end up getting three different triangles. So a five-sided figure results in three triangles. We know that 3 times 180 degrees, because each of those triangles is 180 degrees, will be 540. So the number of degrees in terms of interior angles for this pentagon is 540 degrees. Alright, a hexagon is going to be six-sided. Alright, let's see how many triangles we can get out of that. So I'm going to connect all the non-consecutive vertices. And I notice that I'm going to get four different triangles. Okay, so 6 sides resulted in 4 triangles. And each triangle having 180 degrees, so 180 times 4 gives us 720 degrees. Alright, and that's the sum of the interior angles for a hexagon, a six-sided figure. Now you should be noticing a trend by now. As we take a look at it, the number of sides is always going to be 2 greater than the number of triangles, or the number of triangles is just 2 less than the number of sides. We can kind of use this moving forward. Let's just make sure with one more example, a heptagon, which is a 7-sided figure, and then we'll take a look and make sure that we can confirm that and come up with some equations for any number of sides. So heptagon, 7-sided figure, 2, 3, 4, 5, 6, and 7. Alright, so I'm going to connect all of the non-consecutive vertices that I have. And what I should notice is that I'm going to get 5 triangles. When I count them up, yes, I do have 5. So I get 7-sided figure, 5 triangles. Okay, 5 times that 180 is going to give us 900 degrees. So a heptagon has 900 degrees if you add up all of those interior angles. Okay, for an n-gon, so I said before, that's just going to be any number of sides. So we'll end up replacing n with an actual number. So we'll say n is the number of sides. if n is the number of sides, based on what we've seen in the previous couple of examples, the number of triangles is always 2 less. So I'm just going to take n and I will subtract 2. Okay, that gives us the number of triangles. Now, if I want the sum of the interior angles, I know it's just 180 times the number of triangles I get. Well, here we came up with an expression for the number of triangles. If we multiply that by 180, that's going to give us how many degrees are in that n-gon, whatever number of sides we may be interested in. So n minus 2 times 180. So we've generated an equation that will work for any number of sides. So in summarizing what we just found, we found that the sum of the measures of the interior angles of a convex, so that's being the important part, convex n-gon, is just going to be n minus 2 times 180. Alright, so that's going to be an important equation that we're going to work with throughout this section. And then also an important part, since later on our focus is primarily quadrilaterals, we just want to make note that for a quadrilateral, so a 4-sided figure, the sum of those interior angles is going to be 360. Okay, that's going to be really important later on. We're going to work with quadrilaterals quite a bit. Alright, let's take a look at using this equation for any different type of polygon. So for instance, an octagon. An octagon is just an 8-sided figure, so n is equal to 8 in this case. We want to find the sum of the angle measures for that polygon. So all we got to do is just plug it into the equation that we have. I'm going to replace n with 8. So I got 8 minus 2 times 180 degrees. Alright, so we know for that, really what you're doing is you're taking 6 times 180. And we're going to find that for an octagon, we add all the interior angles up, we're going to get is 1,080 degrees. Okay, so that will be the sum of the angles for that one. For a nonagon, and this will be the last one I expect you guys to kind of recognize in terms of a term. Other than that, we'll give you the actual number for it. Nonagon is just going to be a 9-sided figure, so n will be equal to 9 in that case. So same thing as before. We can just take that to the equation and we can figure out what the sum of the interior angles is going to be. So I got 9 minus 2 times 180, which we know after we simplify that, we really have 7 times 180. And the sum of those angles, we get 1,260 degrees. Alright, so if we add all the interior angles of a nonagon, a 9-sided figure, that's what it'll add up to. Now you can imagine this stuff's going to be useful later on because we're going to solve for some of the unknowns by knowing how many degrees are there in that figure. Alright, so for a 22-agon, so this would be the type of thing we're not going to just use a name for. We know that n obviously is going to be 22, and we can go ahead and we can substitute that into the equation. Alright, so we got 22 minus 2 times 180 degrees. Alright, that will give us 20 times 180, which is a total of 3,600 degrees. So this equation is going to be useful. Without even drawing these figures, without drawing to see how many triangles we're going to get, we're going to know automatically how many, what the sum of the interior angles is going to be.